Hello, good evening. Tonight I'm going to be talking a little bit about the kidney, what it does, and how it affects the blood and the rest of our body. So let's just get into it and start with a little bit of the kidney structure here. So I've drawn out here the kidney. Um, it's protected by the cortex, which is this gray part here. And inside of it, it has the medulla, the renal pyramids, and the nephron, which is the important part we're going to be looking at. And so here we have the ureter, which comes up. It's going to form these things called calyces, and each calyx is connected to a renal pyramid. Here we have the renal artery, the renal vein going to and from the kidney, and that's important because the kidney is actually going to be filtering about 20% of our blood volume every little bit. So the kidney is very important. And if we go into a deeper, smaller level, each one of these lines here in the renal pyramid is a collecting duct that is connected to a nephron. And so we're going to look at the format of the nephron and how filtration and reabsorption work. So when we go down to a deeper level, this is what our nephron looks like. There's two different kinds. There's the cortical nephron and the juxtamedullary nephron. The juxtamedullary is responsible for a lot of water reabsorption due to a greater pressure in the medulla, um, and it's going to go deeper into the medulla. The cortical nephron is mostly going to be in the cortex, and here we have just the basic anatomy of it. The glomerulus here in the Bowman's capsule. This is where blood is going to be filtered through some of the capillaries that they have in here, and it's going to enter into this um, tube where blood parts of the plasma will either be reabsorbed or left in the tube. They'll follow this path and eventually leave the collecting duct as parts of the urine. We've got a couple different arteries coming over here. We have the afferent arteriole, is the blood going towards the glomerulus. The efferent arteriole, which is the blood going away from it, and it's still going to be connecting two different parts of this tubule so that substances that we want to actually keep in the blood that were filtered can re-enter the blood through something called reabsorption. But first I want to talk about that reabsorption. So after filtration, here some substances are going to exit the glomerulus, which we're going to talk about in a second, and they'll enter the tubule. And as they're traveling down this tubule, they're going to be reabsorbed into the blood because not everything that's filtered is stuff that we want to excrete as urine. This first part here is called the proximal convoluted tubule. And here, the biggest factor is going to be sodium, which is actively transported out by the sodium-potassium pump. I think I have a picture down here. And this is the proximal convoluted tubule. There's two different ways that solutes can be reabsorbed. There's transcellular and paracellular. Transcellular is through these cells, and paracellular is in between them. Transcellularly, our sodium that's excreted by the sodium-potassium pump is going to be able to pump glucose into the cell. Also, it's going to help amino acids get into the cell. And because sodium is entering the cell and these other solutes are entering the cell, it's increasing the concentration of solutes inside the cell. So H2O or water is going to follow through aquaporins that are in these cells. And this is the tubular fluid over here, and this is the blood. So all of these glucose, obviously we don't want glucose in the blood, in the urine. If we ever have that, that's a serious problem. Also amino acids. And then there's something called solvent drag here. As the water and the concentration goes towards the blood. Potassium and calcium through paracellular transport are actually going to be dragged along with them, so they're also going to be entering back into the blood. As we get away from the convoluted tubule, we have the proximal straight tubule. This is where our chloride is going to be transported out through chloride leak channels and also through potassium symporters. So chloride is going to be able to exit the cell. So that's about all I want to go over here for reabsorption. Let's look at filtration real quick. All this filtration is going to happen in the renal corpuscle. We just looked at it. This is where the glomerulus is, and that's all inside of Bowman's capsule. So what's going to happen is blood is going to come in from the afferent arteriole, enter into the glomerular capillaries. It's going to cross through, and it's going to be parts of the plasma are going to be filtered out through a couple different ways. Let me try to find that. There's a couple different ways. There's the fenestrated endothelium, so that's the inside of the capillaries. And they're kind of like, fenestra means windows in Latin. So these are like pores in the capillaries. They allow for water and ions or small proteins to cross. The next filter is going to be the basement membrane, which is right on the outside of the capillaries. And negatively charged proteins are going to act as a barrier to keep other negatively charged proteins in the blood that we want to stay there. So that's a second level of defense. And then the third level of defense are these things called podocytes, which are kind of like finger things that are going to be wrapping around the capillary. And these are also going to be a third level of defense to be able to filter out certain things, to keep everything from going into the tubules. One thing that's going to be forcing the fluids in the fluids in the plasma to be leaving is going to be something called glomerular hydrostatic pressure. That is actually similar to our capillary exchange. That's going to be pushing out, but there's also going to be other forces pushing inward. If we come over here to net filtration pressure, our outward pressure minus our inward pressure is going to show our total pressure. So this is going to be our hydrostatic pressure of the glomerulus, so that's inside the capillaries, minus our hydrostatic pressure of the Bowman's capsule, and then BCOP, of course. So these two things are going to be pushing solutes back into it, but obviously our hydrostatic pressure of the glomerulus is higher. It's going to be pushing more solutes out into the Bowman's capsule and then into the tubule of the nephron. This brings us to another topic called GFR. That's the glomerular filtration rate, which is basically how fast the kidneys are going to filter blood. Usually in a normal person, it's going to be about 125 milliliters of plasma per minute. A decreased blood pressure is going to cause a decreased GFR. So if we have less blood going into the glomerulus, less filtration is going to occur. Related to GFR is something called clearance. Clearance is equal to the urine concentration times the urine flow rate over plasma concentration. So what does that mean? That means that clearance, if something is only filtered but never reabsorbed, clearance should equal GFR. If something is filtered but then is reabsorbed, clearance is going to be less than GFR. So we can use the clearance of something that is not reabsorbed to measure our approximate GFR in the kidneys. So one clearance that we use to measure our GFR is creatine. Because the creatine clearance is close to the body's GFR, we're able to use that to measure that. Next, let's head on over to the renin-angiotensinogen aldosterone system. So here I've just created kind of a cause and effect loop. Say our blood pressure goes down, that's going to cause an increase in renin. Renin is going to convert angiotensinogen to angiotensin 1. ACE, which is angiotensin converting enzyme, is going to convert angiotensin 1 to angiotensin 2. And angiotensin 2 is going to have four main functions. One is increasing aldosterone. That comes from the adrenal glands on top of the kidneys. That's going to increase sodium reabsorption and also water reabsorption. So increase in angiotensin 2 means more water reabsorption, which means more yellow pee. Also, it's going to cause a constriction of the efferent arteriole, so that's the arteriole after the glomerulus, causing kind of a buildup. It's going to increase GFR, and our sodium reabsorption is going to increase as well, which will also cause us to retain more water. Ang2 will cause us to vasoconstrict all of our arterioles in the body, which will increase blood pressure, since that's kind of the negative feedback, since the initial causation of this was a decrease in blood pressure. And Ang2 is going to increase ADH release. ADH is going to increase the amount of aquaporins in the collecting duct, which will allow for more water reabsorption, which means water will be retained more. And we're going to talk about that in just a second here, the loop of Henle. So I want to talk about how a couple of different things are related here. So for the most part, our osmolarity in the loop of Henle is going to follow closely to what we have in the cortex and medulla. So as we go down here, 300, 400, 500, 600, then it's going to go back up to about 100 to 75. And normally here, without ADH, here water reabsorption is not going to be possible. So our concentration, our osmolarity is going to stay the same down the collecting duct. But as we increase ADH because of something like dehydration, ADH is going to create these aquaporins on the membrane of the collecting duct, like I was just talking about. So our osmolarity will increase as we go down because water is leaving the cell to balance out and going into the blood. And this is going to cause our pee to be more yellow. And that's how that affects it. So basically, this is the function of the kidneys. Thank you so much for watching, and I hope you have a great night. Thanks.